Understanding algorithm complexity classes in the world of computer science and software development, evaluating the efficiency of algorithms is crucial. Understanding algorithm complexity helps programmers make informed choices, ensuring their solutions run smoothly even as input sizes grow. This article delves deep into the nuances of algorithm complexity classes, exploring big O notation, time-space trade-offs, and practical considerations. Whether you're tackling coding interviews or optimizing production code, mastering these concepts will elevate your skills. Time versus space complexity basics. Algorithm complexity refers to how the resource consumption, typically time or space, of an algorithm grows as the input size increases. This allows developers to predict performance trends and choose optimal solutions for given tasks. Time complexity focuses on execution speed, measured in terms of computational steps relative to input size. Conversely, space complexity quantifies the amount of memory an algorithm requires, including auxiliary storage beyond the input itself. A fundamental concept in complexity analysis is big O notation. This mathematical tool abstracts away constant factors and lower-order terms, focusing instead on the worst-case scenario for scaling behavior. Constants matter little. Big O ignores multiplicative constants because they become negligible for large input sizes. Focus on dominant terms. An algorithm with O, n superscript 2 plus n, complexity simplifies to O, n superscript 2, since quadratic growth dominates linear growth as n increases. Worst-case analysis. Big O evaluates performance in the worst possible situation, providing an upper bound for guaranteed expectations. For example, searching through an unsorted array has a time complexity of O, n, meaning the time required scales proportionally with the number of elements searched. If the array contains 1 million items, in the worst case, the algorithm checks every element. Meanwhile, space complexity depends on variables, data structures, and recursive call stacks. An algorithm that O, n superscript 2 quadratic time algorithms feature nested loops, such as in bubble sort or naive matrix multiplication. Performance degrades rapidly with larger inputs, typically limiting usefulness beyond very small datasets. O2 exponential time complexity reflects brute force approaches used in problems like subset generation or solving puzzles recursively. Such algorithms are impractical for any significant input size due to explosive growth rates. Evaluating algorithm efficiency through examples to appreciate complexity analysis practically, let's examine several algorithm comparisons. Choosing between two competing solutions hinges heavily on understanding their respective growth behaviors. Suppose we're designing a system to process online purchases. One method sequentially scans transactions for duplicates, O, n superscript 2, while another hashes identifiers once, enabling constant time lookups for matches, O, n. Clearly, the latter performs vastly better as transaction volume escalates. Similarly, building a recommendation engine requires processing vast user histories efficiently. A naive pairwise comparison results in O, n superscript 2 computations, but vector similarity calculations using optimized libraries reduce the burden to manageable levels through dimensionality reduction techniques. Databases offer compelling insights into optimizing performance. Query plans often involve indexing mechanisms reducing retrieval operations from O, n, to O, log n. This illustrates how structured data organization can radically transform algorithmic behavior independently of raw logic. Beyond basic operations, parallel computing introduces additional dimensions to evaluate algorithm efficiency. Task decomposition, communication overheads, and synchronization issues create complexity landscapes distinct from sequential processing. Space complexity considerations beyond time memory usage is an equally vital aspect of algorithm evaluation, especially in constraint-limited environments. Applications ranging from IoT devices to browser extensions impose severe restrictions requiring careful allocation awareness. An algorithm operating in place minimizes auxiliary space needs by modifying existing data structures rather than creating copies. Insertion sort exemplifies this principle by maintaining order among already processed elements without extra storage. Conversely, external sorting or memory-mapped files allow processing colossal datasets exceeding available RAM. Though these methods necessitate greater disk access penalties, they enable working with terabyte-scale information otherwise inaccessible in physical memory. Beware of hidden memory footprints from implicit operations like recursion depth tracking or caching intermediate values in functional programs. Even seemingly modest improvements can result in non-trivial reductions across large-scale deployments. Choosing between different approaches based on needs, selecting an appropriate algorithm involves balancing time, space, and correctness priorities according to project goals. Optimization trade-offs are inevitable. The ideal choice rarely exists simultaneously meeting all criteria perfectly. Coding competitions often emphasize pure efficiency, prioritizing fastest execution speeds irrespective of other metrics. However, enterprise systems weigh maintainability against minor gain improvements achievable through micro-optimizations. Machine learning pipelines favor batched computations over per-sample manipulations, leveraging cache locality benefits inherent in contiguous memory accesses. This highlights domain-specific optimizations that transcend general algorithmic principles. If confronted with limited stack depths due to recursion limits, rewriting iterative equivalence avoids runtime errors associated with infinite recurrence chains. Similarly, garbage collection behaviors differ widely across languages, influencing memory management practices effectively. Pitfalls to avoid in analyzing complexities. Misinterpreting complexity ratings can lead to flawed conclusions affecting long-term viability of chosen solutions. Recognizing common misconceptions aids accurate assessments of proposed algorithms' capabilities. Assuming linear relationships between dataset size and computation durations risks overlooking polynomial scaling effects. Doubling inputs won't always simply double execution times. The exponential nature of certain functions surprises novices expecting proportional changes. Confusing average cases with worst-case guarantees presents dangers, particularly concerning security-critical applications. Relying solely on typical performance figures without verifying edge scenarios leaves vulnerabilities exploited intentionally crafted adversarial inputs. Ignoring memory fragmentation issues may cause apparent constant space algorithms actually consuming growing amounts internally behind abstractions. Profiling actual memory utilization complements analytical approximations necessary for reliability assurance. Tools and practices for effective complexity measurement. Empirical testing forms a crucial complement to theoretical analyses in validating complexity assumptions about implemented code bases. Benchmark suites help quantify real-world differences, aligning simulated expectations with observed outcomes. Leverage profiling tools offering detailed breakdowns by operation counts, cycle measurements, and memory access patterns. Visualization dashboards enable intuitive comparisons across multiple candidate implementations side by side. Code coverage instrumentation assists identifying hotspots requiring further investigation during optimization passes. Pinpointing exact segments responsible for majority execution durations guides targeted refinement efforts efficiently. Automated complexity checkers integrated into IDEs provide instant feedback on algorithm properties as engineers write code. These static analyzers flag potentially problematic constructs, prompting preemptive revisions before integration occurs. Future trends in complexity analysis. Emerging technologies continuously reshape perspectives around algorithm efficiency measurements. Quantum computing fundamentally alters traditional assumptions about computational hardness, impacting future benchmarking paradigms. Multi-core architectures demand rethinking parallelizable components eligible for distribution while managing thread creation latencies. Correctly partitioning workload responsibilities proves essential, maintaining gains from concurrent processing initiatives. Cloud-native deployments necessitate considering elasticity constraints imposed by virtualization layers. Network latency-sensitive tasks benefit from collocating logically connected resources, minimizing inter-node transmissions costs. With AI-driven compiler optimizations becoming increasingly sophisticated, hand-tuned assembly-level modifications lose relevance steadily. Focus shifts toward higher-level architectural decisions influencing compiler-generated outputs favorably. Conclusion: mastering algorithm complexity equips developers to build scalable, reliable solutions adaptable to evolving demands. From interview prep to production systems, thoughtful consideration of time and space efficiency ensures robust application designs. Remember, effective algorithm design balances theoretical elegance with pragmatic realities governing deployment contexts. Continuously expanding knowledge base through hands-on experimentation fosters deeper appreciation of intricate interplay shaping modern software ecosystems.